Strogatz graph is actually parameterized by two numbers, C and P. Remember, we were using P to parameterize random graphs and C to parameterize regular ring graph. This is the probability of a link appearing, and this is the deterministic degree for each of all the nodes. Now we're going to use both C and P. We start out constructing a Strogatz graph by constructing a regular graph. Okay, so you got a lot of short-range neighbors, just like before. These are the nodes, and you can add a few more short range. And then here's the randomization step. Randomization has been used in the past in our lectures and will be used a couple more times in later lectures. In today's lecture, the randomization happens by saying that give me any short range link that's existing in this regular graph. What I'm going to do is to look at this short range link and delete it. And instead of this short range link, I'm going to have a draw from a probability with probability P that any pair of nodes, including those far apart, will be connected by a link. Okay, so instead of having this link, I will delete it, and then I'll say, look at any pair of nodes with probability P, add a link. And in the analysis that we will be doing, we'll make a slight modification to say that the existing links will still be there. Okay, so that means we do not delete, we just add links. This will help make the analysis in the advanced material part of the video a little easier. And therefore, if we have 100 short-range links, that gives us 100 chances to establish possibly long-range links. So the question is, how much randomization do we need? Now we know that if there's too much randomization, then it's going to look like a random graph, and therefore it will not have a large clustering coefficient. But if it's too little randomization, the number of long-range links will be so small that will be so close to a regular ring graph. And then the clustering coefficient will be large enough, but the L, our mean, our median distance between node pairs will not be small enough. So as it turns out that a little bit of randomization, a small p suffices. So here I'm plotting p on log scale from 100% to 10% to 1% and so on to 0.1%. As you can see that when p is sufficiently large, then if you look at these two curves, this is the clustering coefficient capturing tri-closure, then it would be too small. Whereas on the other hand, if randomization is too small, L, the median shortest path graph, will be still too high. What we want is for the C curve to bend over, to maintain at a high spot without bending over, and we want the L curve to bend over. So we want an area where we got this part of the curve and around this part of the curve. So the intersection is somewhere in between. This space is a good range. Now this is a numerical example for n equals 600 nodes, and C equals 6, meaning that each node has a degree 6 in the regular ring graph that started the Strogatz graph, meaning 3 on the left and 3 on the right. Okay. For this particular example, it turns out that p in the range of 0.1 to 0.1 to 0.01 will be the right range. That will give you still a sufficiently high clustering coefficient and sufficient low shortest path length. And just to clarify that our y-axis here is the normalized version, meaning we look at the clustering coefficient divided by the largest clustering coefficient that is achieved when p is the smallest. And then we look at L normalized by the largest L. Now, is it a coincidence that for this numerical example, this range of p from 0.1 to 0.01 suffices to give us both of the desirable features? It turns out that's not the case. We can actually write down, as we will do in the advanced material part of the section, the following expressions for C and L. It turns out C is basically behaving like this for what's a Strogatz graph that we just talked about. Okay, it's a function of both C and P, and its impact, the impact of P on this clustering coefficient large C, as you can see, goes roughly like 1 over 1 plus P when P is small. On the other hand, L is approximated by many ways. One of them says it's approximately like a log of NCP over C squared P. So as a function of n, it grows like log n, just as we desired. So we'll wait until advanced material to talk about these analytic formula. And now we want to intuitively understand why. Why is it that if we have a regular ring and then we add some long-range links with a certain probability p, we can achieve both a large L and a large C and a small l? Why is that true intuitively? Well, it turns out that's because our definition, L, as you recall, is about an extremal quantity. This is the median of the shortest distance. I am not talking about all the path between two nodes. I'm talking about the shortest path between two nodes and look at the median of that quantity. In contrast, the C, the clustering coefficient, is about an average quantity. It is talking about the percentage of triad closure out of all the connected triples in the entire graph. Okay, divide by 3 for normalization. I am not talking about an extremal quantity. This is an average quantity, average across entire graphs. And there lies the fundamental reason why what's a Strogatz graph, or the idea of a little bit of randomization, a little bit of random long-range links suffices. The reason is because a little bit of randomization leading to some long-range link is not enough to destroy an average quantity, and therefore you still maintain the large clustering coefficient in a regular graph. And yet it suffices to shorten some path between any two nodes, and that's enough to reduce the shortest distance. And L is only about the shortest distance. Most of the paths are still long. That does not matter. We now got some shortcut long-range links going from this to this, for example. So instead of hopping all the way, locally I can have one shortcut to put me very close to the destination. So I don't mind if the other long paths are still there, because L is only talking about the median of the shortest path. And therefore you may wonder, well, since that's why what Strogatz model works to explain structural small world, why not we make L, define L as the median of the average distances between node pairs rather than the median of the shortest distances? Then it will be a fair definition, fair in the sense L and C will be standing on the same footing. Well, it turns out that we don't need to. Why don't we need to? Because we don't need all the path or the average of the path length between two nodes to be short. When we route, as long as we can find a short path, and a smart enough routing method is going to pick out that path. The functionality implicitly being modeled here is routing, and all we need is some short path. But that means beneath this definition of error is a very basic assumption. It says you can actually have a routing algorithm that can find such a short path. Maybe not the shortest, but a very short path. Now, we just talked about a greedy routing method in social network. We call that greedy social search based on some composite distance metric scores. And let's say if we run this kind of greedy routing method on the social graph, what is the expected length? Let's denote this by little l. Big L is talking about the existence of short path. Little l is talking about the ability to route according to a greedy method and end up with a short path. This is existence result. This is a computability or searchability, navigability result. It says that local information used in greedy fashion can lead you to some short path. If this is true, okay, if this little l is also small, maybe not exactly small as big L, then we're okay. Because it says that, you know what, I don't need to define L as the median of average distances, because shortest distance is going to be discovered. Those paths will be discovered in a practical, greedy, distributed routing method. The question is that true? Well, it turns out that is true as observed in many cases. Now the question is, how can we reverse engineer that searchability result? In other words, how can we have an explanatory model to generate an algorithmic small world?